we're gonna have the recording anyway. So let's get started. Welcome everyone. Sorry for technical difficulties. It seems that we can never get it right. It's my pleasure to introduce Chris Laumann from Boston University, who's only a few blocks from my office right now, streaming worldwide on YouTube and Zoom. He's going to be talking about his research on quantum spin-ice. Welcome, Chris, and thank you for joining us. Please go ahead.
Oh, well, thank you. Thank you, everybody who's come to listen. I mean, this is a Zoom talk. I'm doubtful how interactive it will be, but I'm very happy to have people interrupt and ask questions at any point. And I put a lot of stuff in the talk. And if I don't get through all of it because there's questions, that's fine. I guess if there's no questions, then maybe I'll get through all of it. But that's also okay. What I want to tell you about is work, indeed, that we've been doing on quantum spin-ice over the last few years, mostly contained in these three publications that are, oh, can you guys see my cursor? Yeah, okay. So mostly contained in these three publications here, and you know, along with these guys. So Claudio Castelnuovo, who's at Cambridge, Roderick Mössner at Max Planck in Dresden, Frank Wilczek, who has many affiliations, and then the junior people. So Sid Mornpudi is my former postdoc, who's now a postdoc at MIT, and Sal Pace, who did much of the work in two of the projects here, was a undergraduate thesis student with me here at BU. He went for a year to work on a master's with Claudia at Cambridge, and now he's a starting graduate student at MIT. What do I want to tell you about? Well, I want to tell you about quantum spin-ice, and in particular, the fine structure thereof, which really, by which I mean is interaction effects in the effective description of quantum spin-ice, how big they are, how they might show up in experiments, things that go beyond the first picture of fractionalization in spin-ice. So let me maybe back up and just remind people why. Well, okay, so the first statement is, this is quantum spin-ice. What does it have to do with fine structure? At a very high level, the claim is that quantum spin-ice realizes a compact QED at low temperature. And so it's an interacting theory of light and matter. And we know that QED is characterized by a coupling, which is the fine structure constant, usually called alpha. So let's just review what that is in real physics, not in emergent materials physics. So how do we put together this fine structure constant? Well, we have to go back and ask the opinion of a bunch of old physicists. So Dirac told us that there is an elementary charge, E, and Coulomb, before that, told us that if we have two of them, they will interact with an energy which goes as E squared over their separation R. Okay. Then, a little bit after Coulomb, Planck and Einstein contributed two fundamental constants, Planck's constant h bar and the speed of light. Oh, it just says participants can now see your screen. Could you not before?
We see your screen just fine here. Everything's
okay.
Looks perfect.
Okay. So, and mention we see that combination H bar speed is an energy length. Okay, and that is the same as the dimensions of E squared. And so that means that we can divide them and we get a dimensionless measure of the elementary charge. Essentially, this is just telling us how big a charge is in sort of fundamental units. And it's an interesting quantity. It's only dimensionless as the coupling. in 3+1 dimensions. So in QED and other dimensions, this would not be a dimensionless constant. But it's, which means you can't kind of guess what it is, how big it is on dimensional grounds. And the fact that it is small is extremely important in our universe. So roughly 1 over 137. There are many, many consequences of the fact that this number is just much less than 1. So I was thinking about what some of them are, and as a person who has taught electromagnetism, it occurred to me that the fact that alpha is so small is part of why we teach electricity and magnetism as a separate course from other physics, because actually it doesn't couple very strongly to other things, and so it could be discovered as its own sort of theory that didn't get too mixed up with other stuff. Sort of more technically, there's small light matter interactions, weak photon scattering in the QED vacuum. The famous success of QED was that it gave a computation of the anomalous magnetic moment of the electron, that G-2 was roughly alpha over pi. A kind of beautiful argument, which I believe is due to Feynman, says that the maximum stable element in the periodic table has an atomic number which goes roughly as 1 over alpha. So it's about 137, which if you look at a periodic table, that's actually about right. And that simply comes from asking, if I semi-classically quantize electrons zipping around a charged Z proton in a periodic orbit, and I do Bohr quantization, and then say, but they can't go faster than the speed of light, or else it's unstable, you find an upper bound, and it turns out to be precisely 1 over E squared over H bar C. So there's lots of consequences of the fine structure constant in our universe. Nobody really knows why it's so small. Could have been 1. It's an order 1 number. And there's this great quote from Wolfgang Pauli: when I die, my first question to the devil will be, what is the meaning of the fine structure constant? So I guess this has been an outstanding question for a long time for a lot of physicists. As quantum matter seminar, I don't need to tell anybody here that we think of low temperature materials as providing alternative universes, which can realize alternative standard models if you want. And there's kind of, I guess, 2 versions of that nowadays. I'd say synthetic and emergent, though this is perhaps just words. What I mean by that is that there's quite a few attempts in quantum optics, ultra-cold atoms, superconducting circuit lattices, et cetera, to actually engineer synthetic gauge theories. In fact, just, what is today, the 8th, so just a few days ago, these 2 papers appeared in Science, in which in the first one, the Lukin group realized a Kagame lattice of Rydberg atoms and tuned it into a regime where the Rydberg blockade led this system to realize a 2D Z2 gauge theory. And in a sort of back-to-back paper, the Google group implemented the toric code, or implemented something that realized the ground state of the toric code roughly, in a superconducting circuit. So it's a gate-based model as opposed to a Hamiltonian model. And also went about and measured correlations that arise from having a Z2 gauge theory in the background. Of course, these are 2-dimensional systems realizing this Z2 gauge theory. What we're interested, if we want a alternative universe for QED, is to ideally have a 3D, 3+1 dimensional system, which would realize a full U1 gauge theory. And the primary example that does that, and which motivates everything in this talk, well, okay, whether it does it is something we'll discuss a little bit more later, but which people hope will realize this, are pyrochloromagnets. Actual, frustrated magnets. This is a picture of a piece of a pyrochlor mineral. And pyrochlor as a lattice refers to this lattice of corner sharing tetrahedra that I'm showing at the bottom. Okay, so sort of on the left here, we could say these are synthetic gauge theories. I don't think there's very many serious attempts to build 3D gauge theories in synthetic systems at the moment. There's, obviously leaving out entire swathes of physics, and I don't mean to offend anybody who works on these things. These just seemed like the most salient at the moment to me for this talk. So, okay, what is the plan of my talk? Well, I've got 4 parts. In part 1, I was going to give you guys a review of how you get from spins on a pyrochlor lattice to quantum electrodynamics, an emergent muon gauge theory. And then we will turn to a numerical calculation that we did a year or 2 ago, determining how big alpha is, which oddly, although this system had been studied for a long time, nobody had actually thought to or figured out how to measure the fine structure constant, this sort of fundamental coupling in the theory, until we did it a couple of years ago. And so we'll discuss how big it is. The answer, of course, is already on this slide, but we'll discuss it in more detail later. Then we'll turn quickly to some of the observable dynamical consequences of that. So particularly for neutron scattering in those pyrochlor materials or related materials. Some of you may have, well, whoever among you was attending this seminar last year may have heard Sid give a talk which mostly would have been about this 3rd part. I think last March he spoke in this seminar series. And then finally, at the end, I have a little bonus section, which is on our most recent work, which is also the most speculative, which is about how to find dynamical axions coupled into the emergent QED from coexisting antiparamagnetic orders of certain types, what you should look for in terms of sort of symmetries and materializations, and how that would then be observable, again, in neutron scattering. So that's the plan. Before I go on, are there any immediate questions? Can I encourage people to pipe up if they want me to explain anything in more detail, or discuss anything else? All right. I see that this is the classic talking to myself kind of seminar, so we'll keep going. So from spins to QED. So it is, I believe many of you know, considered obligatory to draw a picture of a triangle with 3 spins on it, and say that frustration in frustrated magnets follows from this idea that, if there's antiferromagnetic links on the triangle, you put an up here and a down there and a down there, and suddenly what does this 3rd one want to be? Okay. I think that is not the true principle of frustration for, quantum or for generally frustrated magnetic physicists. I think the principle of frustration is actually, if spins can't agree on a simple order, then maybe they'll realize an exotic one, and that gives us something to play with. So this is the basic principle that lies in the background of everything going on here, okay? So in order to flesh that out in the context of the spin ice, let's take a look at what these minerals over here, these pyrochlor materials are. So these are magnets. So they're rare earth pyrochlor magnets. They have the general chemical formula that looks something like this. It's composed of a magnetic rare earth ion in the first position. So that's these blue guys in the periodic table. In the second position, there's a non-magnetic ion. That's the red guys, typically. And then there's a bunch of oxygens that are just sort of hanging out and helping to give the thing structure. This picture on the right is actually showing two interpenetrating pyrochlor lattices. So the pyrochlor lattice, the blue lattice of spins, which is the magnetic ions, form a pyrochlor lattice of corner-sharing tetrahedra. There's an interpenetrating red lattice of non-magnetic ions. Luckily, because this is obviously a very complicated picture, we can essentially, for most purposes, ignore that red lattice, just like I haven't even drawn all the oxygens that are peppered through this cell, and just focus on the magnetic spins on this lattice. Now, I'll just point out while we're looking at it, if you're not familiar with pyrochlor, which is this kind of complicated looking thing, it may help you. It actually helps me a lot to realize that if you are more familiar with the diamond lattice, the midpoints of the tetrahedra realize a diamond lattice. And so you can always think of the spins, these atoms, as being on the midpoints of bonds on a diamond lattice. If you're more familiar with that lattice, that might help you visualize things better. Okay, so just a maybe helpful hint. As you can see, there are a lot of different materials, constantly increasing set that can be synthesized and studied in detail. Some of them are sort of very well studied and well established materials now. Some of them are much more controversial. They're grouped maybe broadly into two categories. Classical spin ices, so this holmium and dysprosium titanate, and candidate quantum spin ices. And there's a bunch listed here, and maybe there are others. So the classical spin ices are called classical spin ices for details that we'll see momentarily, but they've been studied very well. At intermediate temperature regimes are well described by a system of interacting spinons. In this context, they're usually called magnetic monopoles, which have fractionalized from the underlying spins. But at zero, as you lower the temperature, they don't, quote, become quantum because they end up, both of these materials, just order. So they go into symmetry breaking phases and leave the sort of exotic frustrated magnet regime. The candidate quantum spin ices, well, they're candidates because these ones, they're all different. The details of what's known is different, and what's debated is different. But basically, they have controversial order at low temperature. So it's not clear whether these order or not, and maybe they remain kind of fractionalized spin ice materials all the way down to low temperature. So these are the ones that are, maybe we'll actually realize this QED that theorists hope for. So that's as much as I plan to say about sort of real materials. Now I want to turn to essentially explaining the toy model of, where does the name spin ice come from? What's the basic phenomena? If you've never seen anything about ice before, then hopefully this will be the thing you take away from this talk as like the way it works, because actually it's a really beautiful story. I have to say the reason I didn't work on spin ice until a few years ago, and I think the reason I started working on it is because I just think this is such a beautiful sort of geometric picture that emerges from it. Okay, so here is the essential picture of spin ice. We suppose, here's a piece of pyrochlor lattice, that there is a easy axis spin on each of these atoms. And it's a two-level spin. And the two levels, as I said, easy axis, correspond to pointing along the local 1, 1, 1 direction or against it. Okay, and what that means is that what we traditionally do is define a local quantization axis for the spin. So we call SZ the local direction that goes from one between the adjacent tetrahedra. For this blue one, it's along here. For the red one, it's along here, and so on. So there's 4 different axes actually. And SZ being plus half corresponds to a spin pointing from, say, this tetrahedron to the adjacent one. And if it's not clear from the picture, this is a well-defined thing to do across the whole lattice, because actually there are 2 types of tetrahedra. You could say an A and a B, and they alternate. It's bipartite, just like the diamond lattice is a bipartite lattice. And so you can just define SZ being plus to mean that the spin is pointing from an A tetrahedron to a B tetrahedron, for example. That's a consistent choice. In the spinized type materials, the dominant coupling is an exchange coupling of Ising type, in this basis, ZZ type, with a coupling that we call JZZ across all nearest neighbors. Okay. Now, because on each of these tetrahedra, all 4 spins speak to each other with the same coupling, we can quickly rewrite this as a sum over tetrahedra. And for each tetrahedra, we take just the sum over all the SZs and square it. Right? This generates all of the terms pairwise on this. And I've dropped a constant in saying that's an equality because SZ squares to a quarter. Okay. But now we immediately know how to minimize this Hamiltonian. Once I've written it like this, I just want to make the total Z spin on each tetrahedron as small as possible. Now, since each of these are plus or minus, that means I want 2 pluses and 2 minuses, right? Or that I want 2 in and 2 out of each tetrahedron, okay? Slightly more formally, I can also equate this with saying that the sum of the SZs on a tetrahedron is actually, up to a sign, the lattice divergence of SZ, thought of as a field that, you know, on actually really on the diamond lattice, that the divergence is how much is coming out of each of these tetrahedra, right? So it's a field defined on the tetrahedra. And just because of the way I defined what SZ being plus 1 is, this is just equality because I square it. So on A and B sublattices, I get rid of the minus sign. Okay, so from that trivial manipulation, we've learned that the ground states are 2 in, 2 out states, or equivalently divergence-free states. Those are all the same thing. And we know those are the ground states, by the way, because, you know, if we have 2 in, 2 out, this sum is 0, and you can't get less than 0 for something which is made of a sum of positive, you know, squares, right? So we really know those are ground states. Okay, but many states satisfy 2 in, 2 out. Let's look. There's another one. So I started with 1. These arrows satisfy 2 in, 2 out, and I've rotated 2 of them, and this also satisfies 2 in, 2 out. And I could also rotate those ones, and that also satisfies 2 in, 2 out. And this 2 in, 2 out rule was originally postulated by Bernal and Fowler in 1933 to describe the allowed configurations of hydrogen bonding in water ice, which is why these are called ice states. And 2 years later, Linus Pauling worked out that actually there were exponentially many states that would satisfy this 2 in, 2 out rule. So exponentially many ice states. And there's a very simple estimate he did. It's kind of a mean field entropy counting. And it goes like this. So the number of states is basically the number of 2 in, 2 out states on each tetrahedron. So that's 4 choose 2. There's 4 spins on each tetrahedron, and you have to pick which 2 point in, which is 6. So you have 6 to the number of tetrahedron states. But if you did that, then neighboring tetrahedra might disagree in that choice about whether a spin was supposed to be pointing from A to B or B to A. And so you have to cut down that overcounting by a half, which is the probability that they would disagree, for each of the bonds between two tetrahedra, which is there's 2 per tetrahedron. And that's it. That's this estimate. 60n tetrahedra times a half to the number of bonds, which is 2n tetrahedra. And if you take a log, you get an extensive, what's called isentropy, which is the number of tetrahedra times the log of 3/2 in this estimate. And I will mention that this was measured, a year or 2 later, calorimetrically. This residual entropy of water ice was measured, and this estimate was good to a few percent. It's been refined a bit since, but it's surprisingly good for such a simple argument. So now what? Well, we have this divergence-free spin field. Of course, there are configurations where there's divergence. Those are defects in this 2-in, 2-out rule, and we call them spinons. So spinons are defects in the ice rule. So here, again, I've drawn some arrows for you, which are 2-in, 2-out on each of those central tetrahedra. If I flip that central spin, then now there's a 3-out, 1-in tetrahedron and a 3-in, 1-out tetrahedron. I can simply define the charge on the tetrahedron as, how many are pointing out minus how many are pointing in, or the divergence itself is the charge. And notice that this is constructed, right? I can't violate this. It's clearly a Gauss's law, but it's inviolable because it's how I defined what a charge was from this. Okay, great. So this would not be of much interest if it weren't for the fact that the spinons really can separate and become the natural quasi-particle excitations in the system. So if I flip that blue arrow, I've now healed the tetrahedron that had the plus charge, but I've moved the plus charge over to this tetrahedron over here, which would now be 3-out, 1-in. And if you recall our Hamiltonian, the Hamiltonian just was a sum over the essentially tetrahedra of the charge squared. Since I haven't changed the number of places with charge, this cost no energy. So I'm able to move these defects apart with no energy cost. So we say that the flips, I started with a spin flip, it fractionalized into a spin-on anti-spin-on pair because those endpoints can separate. This is the starting point of classical spin ice, that the right way to understand those classical spin ice materials is in terms of dilute gases of spin-ons and anti-spin-ons. Okay. And I should say the full story of the classical spin ice is a little bit more complicated because there is actually an entropic cost to separating the spin-on anti-spin-on pair. You remember there's an isentropy, and I'm going to reduce it by creating these defects and separating them. And it turns out that that entropic cost itself is governed by a Coulomb law, which goes as 1 over R. So this is already kind of a classical fractionalized Coulomb spin loop. Okay. Any questions about that? All right. So what makes it quantum? Well, as I mentioned, the ground state manifold has this entropic degeneracy in our nearest neighbor Hamiltonian, and the third law of thermodynamics forbids that. So something's got to happen as you lower the temperature. In real water ice and in those classical spin ices, the system simply orders, and that's kind of the end of the story. The entropy freezes out by the system ordering into some simple symmetry breaking state. In the ideal quantum spin ices, the idea is not that the system orders, but that off-diagonal terms that are smaller than the JZZ term will lift the exponential degeneracy of the ice manifold and lead to some kind of essentially unique ground state, which is some big superposition of those ice states. Okay, so how does that work? Well, there are many terms that you could add here. The simplest to analyze, and for me to sort of take you through, is this the simplest one that's also symmetry allowed, is this two-body J plus minus term, S plus S minus on nearest neighbors. And because what this does is it flips two spins which are pointing end to end. Because of the way we've defined what plus and minus mean in our local basis, it's you sort of follow a spin arrow from one tetrahedron through to the next, and then follow another one to the next one, and those two you flip coherently, and it creates a spin-on anti-spin-on pair because you flip two spins. And that, of course, takes out of the ice manifold. You pay this big JZZ energy, but if you work perturbatively to project this back down into the ice manifold, what you would find is that at third order, you can create a spin-on anti-spin-on pair, hop the spin-on around, and re-annihilate it with the anti-spin-on you left at the beginning. The shortest cycle that can happen on in the Pyrochlorite lattice is length 6. They kind of look like, these cycles look like hexagonal plaquettes, but they're a little bit crumpled. They're not flat in the plane that they sit in. They sort of go up and down a little bit. What this corresponds to is really a ring exchange. That is that you find a sequence of 6 spins which are pointing head to tail around one of these length 6 cycles, and you just reverse all of them. And that's the smallest thing you can do and remain in the ice manifold. And so it's the thing which is generated perturbatively. Okay. Good. So actually that Hamiltonian I just wrote is already essentially describing a system which is going to be described by a Yuan gauge theory, but I can make it look familiar, or maybe more familiar, using just a kind of formal trick. So what I do is I'm going to soften the 2-level constraint, the spin half constraint, using twisted rotors. So I'm going to replace each spin where SZ can take values plus or minus a half, and then these raising and lowering operators S plus S minus, by a little rotor, which is a particle, a phase A, living on a ring. And by twisted, what I mean by that is that the conjugate momentum is not going to take values, or angular momentum is not going to take integer values, but it's going to take half integer values. And I can do that just by twisting a boundary condition on each of those rings. And so now I say that conjugate momentum, I call it E, and it's a half integer, and A is the phase. And I write down, as essentially exact rewriting once I do this relaxation, that Hamiltonian, which I called H ring a minute ago, takes this form. It's G sum over those hexagons cosine curl of A. And the cosine of the curl there is coming in because, remember I had an S plus S minus around the 6 links on a hexagon. That's becomes e to the plus or minus IA summed around the hexagon. So that's a curl. And then because it's Hermitian, I have to add the conjugate, and I get e to the plus and e to the minus. I get a cosine of the curl. Okay. What is this gamma I've introduced? Well, I need to have some this is the kinetic energy of those rotors, right? And so I'm just for the moment, let me just introduce it. I just say it's some coefficient. If I had small gamma, then the fluctuations of the momentum are large, and the fluctuations of the Oh, somebody's raised a hand.
Yeah, hi. Can you just explain how you got the rotors again? I missed that part. Or if you could just go over that one more time.
Sure. So the idea is that I have a two-level degree of freedom, and I want to come up with another way to write a two-level degree of freedom. And so I can do it by saying, let me imagine that there's a rotor. So that's just a particle living on a circle. Okay. And a particle living on a circle has a position, a phase, and a momentum, right? But because it lives on a circle, the allowed momenta are quantized into integers. Say the circle has, I don't know, circumference 2 pi, then literally the angular momenta are integers. The allowed momenta are integers, right?
Right.
So now if I, instead of taking periodic boundary conditions on that rotor, take anti-periodic, I'll shift those angular momentum to be half integers. Okay. So for the moment, what I've done is replaced a variable which is SC is plus or minus a half by a variable which can go plus or minus a half, but also plus or minus 3 halves, plus or minus 5 halves. Okay. The S plus minus operators, if I am restricted to the plus or minus a half states, really are exactly the same as these e to the plus or minus IA operators, which raise or lower the angular momentum.
No, so are you replacing all the spins with rotors throughout the lattice and on every side of the lattice?
Every single one, but it's a formal trick, and you'll see how I recover it. But yes, I take every spin and I just replace it by this formal object, and it's mostly so you can see how gauge theory emerges.
Okay.
But yes,
but you're not changing the theory in the process?
No, this is, well, okay. So at gamma goes to infinity, this is actually matrix element by matrix element, an exact rewriting of the spin Hamiltonian.
Oh, okay, all right. It's a
not
trick.
changing
it's a
anything.
trick. Yeah. All right.
Yeah, it's a trick. So at finite gamma, this is changing the theory a little bit. Well, it's changing the Hilbert space. It's clearly changing the theory, right? But the microscopic theory. But the reason this is a useful thing to do is it's very suggestive, because if I could go to small gamma, which of course is not where I want to be, then the kinetic energy, that's basically saying that I have like heavy rotors, right? And they tend to lock their position. So I can just, find the ground state of this curl, of this cosine, and expand around it. And I would get something like a curl squared by expanding the cosine. And of course, the kernel of A squared is the magnetic field squared, B squared, right? On the lattice. And the conjugate thing is E squared, which I got. So this thing, if I can expand gamma, is basically E squared plus B squared, where I have a lattice, literally a lattice gauge theory made out of a vector potential and conjugate electric field. And so you'd say, oh, I got photons. This is a Maxwell theory. Or at least, and that's true at that level. But the problem is that you have to take gamma to infinity to recover the spin half constraint. So this is not really an acceptable thing, but at least it makes it look suggestive. In order to check that the system remains in the Maxwell phase, which we found at small gamma, you basically have to do numerics back in your spin half constrained model. So you shouldn't really go to rotors. In fact, it just makes your life harder once you're going to do it numerically. You really want a two-level system. And so you do it, and many people did it. This is work going back almost 20 years now with various techniques. You find that there are indeed emergent, linearly dispersing vector-like transverse excitations. So you get a photon, well, a pair, because there's two polarizations. Now, what do those correspond to in terms of physics? It's actually like sort of coherently propagating modes where the ring exchanges are resonating back and forth. They're kind of hard to visualize in that language, but the effective description is just that there's a photon with a linear dispersion. And what we have is that photon, well, the source for the electric field which was the divergence of SZ, is the spinons that we talked about a minute ago. So this is a theory which has spinons, which we could call little e charges. So notice I'm using lowercase a, e, and b to indicate all of the electric, magnetic, and gauge fields which are in the effective theory here. They are not the same as the external electric and magnetic fields with which you might be probing the material. They couple to those in certain ways, but they're not the same, and it's important to remember that. So you have a little e charge, which is a spinon, you have a photon, and then you have this little b monopole. So this is not a feature that actually is very well established numerically either, but everybody believes it's there. This is a magnetic monopole is necessarily an excitation in a lattice compact gauge theory. This is not part of our usual universe. Also, the fact that the charge has this enormous gap and can go faster than the speed of light and so on, not part of our usual QED universe. But there is an emergent Maxwell theory. So any questions about that? Or any more questions about that?
Well, I guess I have a very naive question. I mean, when you say you do the numerics, you just build a model with some number of lattice sites, build the Hamiltonian, and then plug it into some Monte Carlo algorithm or something like that?
Well, there's a few different approaches. So indeed, you can do on, this ring exchange model is mostly what's been studied, plus perturbations to it. You can do quantum Monte Carlo for a certain sign of G. There's no sign problem, and that's what the largest scale studies are. You can also do, as I will show you in a few minutes, exact diagonalization and see evidence for the Maxwell theory as well, although on somewhat smaller systems. I think those are there's a few different variations on the QMC that's been used, but I think those are the primary techniques that have been used numerically to study this microscopic model.
Okay, but the ring exchange term has to be added in by hand into the numerics.
You mean compared to this?
Yeah, I mean, if you just start from the,
I think actually that's a good question. I'd have to go back and look. I think you can start with this, but in fact, I'm pretty sure people have studied this without projecting into the ice manifold. So this would generate the ring exchange.
Okay. Okay. Thanks.
You probably, to make your QMC converge, have to know the ring exchange is going to be an important process. But I think you can study this initial Hamiltonian in an unconstrained system.
Okay, thanks.
In exact diagonalization, you couldn't, because you would be too severely constrained by the size of the Hilbert space. But in QMC, I think you can do it. Okay, so actually, this is a very relevant question, because the next thing is a kind of numerical result, which is about how big is the coupling in that theory. I just showed you what the three kinds of elementary excitations are that we believe emerge in that low energy theory, but they're coupled, and they're coupled by QED, by an effective QED, but nobody had checked how big that was. So how big is the fine structure constant? Well, I'm writing the long wavelength Maxwell theory here in a slightly unusual choice of units, simply to point out that there are two parameters that come out. So here I've written this in units such that the fine structure constant, the coupling, actually comes out in the denominator of the Lagrangian out front, and the speed of light is explicit. This is what we'd like to extract, these long wavelength parameters, from this lattice rotor theory, and actually more specifically, this lattice rotor theory at gamma to infinity, where it's the ring exchange model. And as I mentioned before, for small gamma, you can expand the cosine. It's a quadratic theory, and it's a little bit of algebra, but not terribly hard. to show that the resulting speed of light is given by the square root of gamma g, which makes sense. Gamma and g are energies, so the speed of light, sorry, I've dropped a lattice constant. So this is a lattice constant times root gamma g. Or another way to say it is that if I scale up the Hamiltonian, I expect the speed of light to just scale up with that. So it has to be somehow proportional to the energy coefficients. Whereas the fine structure constant is the dimensionless combination of the two things. It turns out to be the square root of the ratio, okay, of gamma and g. But for spin half, as I've said before, gamma goes to infinity. So what's going on? Does the speed of light go to infinity? Does alpha go to infinity? No, they're both finite. And you need numerics to deal with the sort of infinite renormalization that you would get from trying to treat it in this way. How do we do it? Well, we're actually going to look at this alpha z squared over h bar c. And what we want to do is measure the two parts, e squared and c. Now, the speed of light is actually the main thing that was checked by many of those early numerical works. They extracted the speed of light in just establishing that there was a linearly dispersing mode in the system, right? So that actually has been known a long time. But that leaves us with the question of how do we get E squared? How big is the elementary charge? So you might think that what you should do is put two probe charges in and ask how much energy they cost and how that varies with how far apart they are, right? By the Coulomb law, E squared over R. But the problem is that, you know, you're going to work in a finite computational cell, and there are just enormous finite size effects. By putting in these probe charges, you lose translation invariance. You have to be able to separate them a long way to get beyond lattice. If you put in a periodic boundary system, then the dipole fields actually do much more complicated things than they do if you're in a non-periodic system, because these electric fields can go around the periodic boundaries. So this is not a good approach. And I think it's essentially why this hadn't been measured before. So the trick is that in the ice manifold, the electric flux through the periodic boundaries is topologically conserved. Okay, so let me explain what that means, and that's what we're going to use. So I'm showing you a picture of a configuration of arrows which satisfies 2 in, 2 out everywhere, I believe. Take my word for it. I mean, I guess you guys can try to drive yourselves blind by checking every point, but this satisfies 2 in, 2 out, so it's an ice state, just drawn on a square lattice. If I create a pair of excitations, a spin-on, anti-spin-on, by flipping a spin, and then I drag by flipping a sequence of spins, say the anti-spin-on around through a periodic boundary, and then reannihilate it, I've left behind a string of flipped arrows, which indicates that an extra unit of elementary electric flux is actually piercing this periodic boundary now, compared to the configuration before I did this process. And I know it's the elementary electric flux because it is precisely the flux that was carried by the elementary charge as I dragged it around, right? I can count that or measure it by looking at these Gaussian surfaces which cross the lattice, and you can just ask how many spins point left or point right through this vertical one, add it up, you'll get a number. Similarly, up or down through the horizontal one, add it up, you'll get a number. Each of those numbers is a conserved quantum number. It's a topologically conserved number in the ice manifold. So if I can only do local moves, ring exchanges on these squares, without being able to actually drag a spinon through the whole lattice, then these two numbers are conserved, 1 and 0, phi 1 and phi 2. And that means that I can use them to my advantage, right? I can basically tell that an extra unit, elementary unit of electric flux has threaded a boundary by looking at what this quantum number is. If I'm in the Maxwell phase, so what I just said has nothing to do with actually being in the Maxwell phase per se, but if I'm in the Maxwell phase, then in the ground state, I expect that this electric flux, this red line that I left behind in my classical configuration, actually uniformly delocalizes, right? Because I'm in a phase where I just want to spread out electric field as much as possible in a uniform system. It's just electrostatics. And so in a three-dimensional volume, there's 3 of these flux sectors. I fix the integer flux going through each boundary, and then I find the uniform electric field, which actually would have the appropriate electric flux through those walls. And I can get a particular way that the energy density scales quadratically with the electric field integrated over the volume for a particular volume. And from that, and then numerically measuring the energy as a function of the flux quantum numbers, and looking at essentially the energy as a function of the square of those quantum numbers, appropriate with this vector Q here is just dealing with the shapes of my periodic cells. I can extract a measure of E squared, and from the dispersion of the ground state energy as a function of momentum, global momentum, I know that if I increase the momentum of the system by 1 unit, that should correspond to the ground state plus 1 photon. So I can measure the photon dispersion and use that to get the speed of light. I can divide them, and I get something around 1/10. Let me make a few comments about this. This is constrained DD up to 96 spins. We can get that big because of the ice constraint on just this pure ring exchange Hamiltonian for the moment. You may say this data looks very noisy. It's actually a little bit misleading plotted like this. Yes, there's a fair bit of scatter in the point. So what are we varying here? We're varying the geometry of the computational cells. So we're making different parallelepipeds in order to get as much data as we can in the finite sizes we're limited to. And you do indeed see some fluctuation around this central trend. What you don't see in the way this is plotted is that actually the outer boundaries of this are very much outliers. Almost all of the data is actually points are actually piled up on this red line. So it's a much better fit than it looks visually, actually, in this, a much tighter fit. Of course, these are limited system sizes. Perhaps one could use a more sophisticated quantum Monte Carlo technique to get to bigger sizes. But actually, there's a limit to how far one should push this. The main point is that we get about 1/10, okay? That is, I claim, the natural scale for the fine structure constant in this deconfined QED phase, whatever your detailed microscopics are. So what do I mean by that? I don't actually think that the true systems are governed by that pure ring exchange Hamiltonian. And in fact, we added various microscopic perturbations that we could deal with and played with them. If you vary microscopic couplings, then alpha will vary. It's not fixed, right? It's in the long wavelength sense, there's a marginal coupling. And so it's a little bit like, it's actually very analogous to the dimensionless stiffness in 2D Kosterlitz-Thales phase, that if you vary microscopics, of course, you'll vary the stiffness. If you vary microscopic couplings here, you're going to vary the fine structure coupling alpha. And as you vary it, it varies on the scale of 1/10. So it goes, you can, by suitable fine tuning, tune it all the way down to 0. There's a Roxar-Kivelson point there, which has fine coupling 0. And that's the simplest way to get it to 0. It's actually also a cross-check on our numerics. And you can tune it up to about 0.2 with the right kinds of inner microscopics. And beyond that, whatever you do, whether it's 0.2 or 0.22, okay, I'm not going to commit. But beyond that, what happens is that actually you always go into an ordered state. And we found that numerically and later discovered that Carty, 40 years ago, had proposed that there's actually a universal upper bound on alpha in pure compact QED, which comes because if alpha gets big, these B monopoles I mentioned actually interact very weakly and they unbind. Just like in the Koslitz-Thales phase, the vortices at some point have a universal value of K at which they unbind. He argued there was a universal value of alpha above which these would unbind, and that causes the system to go into some other phase. What that value is not known. It's less than a quarter, and there's a bunch of numerics across lots of different models which give roughly similar alphas at which they go, at which they leave their QED phases in different kind of lattice gauge theory models. So our interpretation of that is that the natural scale here is a 10th variable on this range of 0 to 0.2. Anything significantly smaller is fine-tuned. So 1 over 137 is quite fine-tuned. And this has nothing to do with, RG arguments, logarithmic flow. All of these things are details if you are already becoming fine-tuned. Okay. Okay, so that's part 2. I guess it's a matter of taste if you think that's big or small. 0.1 is a number that most people would say is still something you could perturb in. And that's probably true to a pretty good approximation. But it's 10 times larger than it is in our universe, where it's 1 over 137. And that means that the interaction effects in this emergent QED should be significantly stronger and more observable, because this alpha is not 1 over 100, because it's only a 10th, and maybe even larger, depending on the details. So that brings me to the third part of the talk. How am I doing on time? Because I see I'm already after 4.
How much time you think you need to finish?
Well, it depends. I can move quickly or slowly or whatever. I don't know what time we started exactly.
We started 5 minutes past. So let's finish part 3 and keep the pace as it is. I think it's fine.
Okay. Fine. So great. So and this is the part which has the most overlap with what Sid Morampudi talked about last year. So maybe I will move briskly. So what would some of these consequences be? Well, this, to be honest, in terms of our personal research journey, we started by thinking about how neutron scattering could probe the dynamic structure factor of spin ice, and in particular that spin flip scattering of neutrons should probe spin-on anti-spin-on pair production, and that there should be interaction effects in that. And that's actually what this paper from 2020 was about. And all of the interaction effects in that we discussed are dependent on how big the coupling is. Fine structure constant alpha is basically the front factor, or alpha squared, for all the effects in there. And so that's why we said, well, what is it? And we realized nobody had ever gone and calculated it. So that was what motivated actually us to then go and calculate it. So I'm telling you the story in the, I think, more natural, logical order, but we came at it from this direction first. So let me explain that, or maybe it's clear. If a neutron comes in, scatters off your sample, and flips a spin, then it contributes some energy and momentum, and that spin flip to the system. We know that flipping a spin creates a spin-on anti-spin-on pair. That's like pair production in the effective theory. And so we should be able to probe that, okay? In order to understand what comes out, let's think about the important kinematic ingredients. I have a linearly dispersing photon, and I have this spinon and a matching anti-spinon. But this theory is not Lorentz invariant. Okay, so the photon in particular is set by a ring exchange scale. The speed is set by a ring exchange scale. On the other hand, the bandwidth of the spinon is actually set directly by that J plus minus term, which can hop them. So we expect that the speed of light is quite small compared to the bandwidth of the spinon, or another way to say it is that C is small and the spinons can go really fast. And also that alpha being about 1/10 means that the spin-on photon and spin-on interaction should matter. Okay, so to see how they would matter, let's first think about what happens if we just set alpha to 0. Well, then what you expect to see in the neutron scattering would be that would be something like this. So the idea is that you need to provide, twice the gap, and you produce the energy for a spin-on and anti-spin-on. And above that gap, you'll start producing pairs, right? And so you'll start getting absorption or scattering response. And as you increase the energy, say at Q equals 0, you are you have center of mass momentum for the pair 0, but you are increasing the relative momentum of the pair. And of course, that relative momentum can be pointing in any direction in 3D. It's just constrained by the amount of energy. And so you get something which the number of states consistent with that energy and center of mass momentum will go as the density of states in 3D, which for a quadratically dispersing particle like that grows as a square root. And in particular, in this approach, you'd also find that if you increase the center of mass momentum, that is the momentum which that the neutron is providing to the pair, that essentially just goes into the center of mass momentum, which is decoupled from the two-particle problem. And so all that happens is that the whole turn-on has a parabolic bottom, and there's a square root, and the whole thing just shifts upward. Okay, great. So this is kind of this is already something. This is saying that my spin-on is not creating a single excitation, it's creating a pair. But it's a relatively featureless sort of blob near zero momentum. So what happens due to interactions? Well, lots of stuff, and I'm only going to quickly sketch it. So let's first think about Q equals 0, where the center of mass momentum of the pair is 0. That means that you're creating them asymptotically, they'd be flying directly apart from each other. So if we are near threshold, then at least once they're far apart, they don't have very much energy. And so we're going to neglect radiation effects for a moment. And we would have an effective problem for these two spin-ons, which is Q squared, that's the center of mass momentum, their relative momentum, but now they attract each other with the Z squared over R, and also potentially short range potential as well, coming from lattice effects. At a very high level, those final state interactions actually matter. The way you know that, without me doing any calculations, is you can think about what happens in semiconductors absorbing photons, where if you have a particle-hole pair production for a non-interacting particle and hole pair, you have the exact same story I just told you, that you'd have a gap and then a square root turn-on of some absorption. But in fact, the electron and the hole attract each other. They can, in principle, produce a Rydberg-like bound state, which would be a sharp line in this, and they can have higher bound states, which give them some ringing below the gap, and that continuously turns on into this ionizing spectrum, into this sort of ionized spectrum up here. So those are respectively the Rydberg bound states, and this big enhancement, even above the ionization threshold for the absorption here, is called the Sommerfeld enhancement of those separated electron hole states. So those final state interactions really matter, potentially. Actually, something that doesn't happen in the case of photons and excitons in semiconductors is that we can, because we're probing with neutrons, we can probe with significant center of mass momentum. And there is, and so you have to actually think about a problem where these electron and hole or spinon and antispinon are interacting as they fly apart and also have a net motion parallel. And there is a correction to the Coulomb law, actually comes in at the leading order in velocities over speed of light, which is a current-current interaction. This is basically the magnetic field created by a moving particle acting on the velocity current of the other particle instantaneously. And this is actually, this term is called the Bright term. Herr Bright worked out the quantum mechanical version of this interaction just a couple years after the Schrodinger equation and used it to compute corrections to the fine structure of certain atoms. It actually, I don't know that anybody's ever analyzed it or that it's come up in any other particular context, for example, of pair production for ionizing states. But the dominant effect here is that it reduces the long range attraction with the center of mass Q, okay? And what that leads to is that the speed of light, the dynamic structure factor has instead of a square root like turn on, it has a step function like turn on. That was that enhancement that we saw, the Sommerfeld enhancement, which is in turn suppressed by the center of mass momentum. And then maybe the most sort of, actually, maybe I should have started here. The simplest effect is that if the momenta of the spinons gets too large, greater than mc, where c is the emergent speed of light and m is the mass of the spinon, then they start Cherenkov radiating. They start emitting into that emergent photon field. And that leads to a finite lifetime for these spinons. And it makes that band edge very soft because it's made out of things that become very diffuse. So putting that all together, you get a much more detailed picture of the structure of this neutron scattering near zero momentum. So there's a gap, but now there's Rydberg bound states. They actually merge into the continuum as you approach this Cherenkov threshold. Beyond the Cherenkov threshold, the boundary gets very soft because you're not really creating a two-particle state in the final state. You're creating a two-particle state plus lots of photons. And there's a big enhancement of the density of states near zero momentum at the threshold, which is coming from that, the Sommerfeld enhancement that I didn't really explain where it came from, which also has some characteristic Q dependence, all of which gets softer as basically you move away from Q equals zero, okay? So this is, this is a lot of structure. It's very detailed. And in real materials, the relevant energy scales are small. Being able to see all of this would be, I think beyond what's realistic for near-term neutron scattering. On the other hand, the basic signature that you should see hard response right near Q equals zero, which turns off as you approach this Cherenkov threshold, this actually, I think, is not totally crazy. That just sort of qualitative picture that's quite different from what the non-interacting picture of spinons would give you. Is a plausible target. Okay, so I guess I've run a fair bit over time. It's 1:15, so I can skip dynamical axions unless people really want to hear about it. And just go to my conclusions. Quantum spin-ice. So the first thing I told you about, maybe too slowly, since I didn't get to the axions, I don't know, was that quantum spin-ice is a compact gluon gauge theory at zero temperature. That is characterized by coupling, which is large, okay, is a 10th large, matter of taste, but it's large compared to 1/137. And it's tunable by microscopics, almost anything should make it vary, but it will always be on this scale of 0.1. Anything much smaller than that would be fine tuning, not just sort of squeezing it. And that has observable consequences in neutron scattering. All of these effects I talked about are only there because alpha is non-zero. And they are, the size of these effects is proportional to alpha or alpha squared, depending on exactly what we're talking about. And what I skipped was telling you about how you could imagine observing something that behaves like an axion in this emergent theory by having a coexisting magnetic order of the right type and some breathing on the lattice. There's some symmetry arguments. And then once you have that, actually, that leads to some qualitative signatures in neutron scattering that wouldn't be there otherwise. So that was the part I skipped over, the most recent work. Anyway, thank you.
All right. Thank you, Chris, for a beautiful talk. Very clear, very detailed. I'm happy that I'm sure my students learned a lot today. So we have, very little time, but let's use it for some questions from the audience.
Sure.
Noah, please go ahead.
Hi, Chris. I'm trying to understand the analogy. Well, it's not an analogy, but the picture you gave comparing Carty's argument about the existence of a critical point at large alpha and the case of just an O2 rotor chain, has this unbinding of vortices. In particular, what I'm thinking about is, there's this universal jump that you see in superfluid helium films at finite temperature in 2 dimensions. And I'm wondering if there's some analogous thing, if it maybe finite temperature or in some other limit relevant for this this large alpha transition.
Actually, that's a good question.
Maybe I can ask a simpler. What's Carty's argument?
The universal jump is a step beyond just saying that there's an upper bound on the stiffness at which things unbind, right? Or a inverse stiffness. So that I don't immediately know what the analogous statement would be. No, and I'm not sure. I'll say that Carty's paper, that paper from 1980, is beautiful. So, and if there is an analog, he may have discussed it, but I'm not remembering it. It's been a while since I looked at that in detail. And nothing jumps out at me. I have to say, what's on the other side of this condensed phase is something we did not worry about too much in doing our work. On the other side of this transition is not something we worried about too much in our system. It's very hard to tell what you actually, it's some kind of symmetry breaking order. It's kind of clear in the numerics, but we did not try to figure out what it was and how to characterize it and whether there'd be a universal jump of some sort or anything like that. That's, that is beyond what we thought seriously about.
And I guess the other question is, what are these pyrochlor oxides? What do they look like? How big a crystal can you grow? What's their typical optical band gap? Not the spinon band gap, but like shine some light on it. How low a frequency do I have to shine so that it's transparent?
Well, I think they look like that. That's actually a picture of one of them. That's a natural pyrochlor. I don't remember exactly which one it is. It's a bit variable. So some of these you can get big chunks of. Some of these have been synthesized in powders, and then later people figured out how to do bigger single crystals. They're all a bit different. These compounds, I think, are all pretty big band gap insulators. So see, that's black. But there are some of them. So if you put if this B is an iridium, I know in some of those materials, there's even conduction. So you have a fairly magnetic sort of, these rare earth ions are not really contributing to the conduction. The conduction is mostly on the iridium lattice, but those two orders couple, or the physics of the conduction and the magnetic ordering can couple. There's a bunch of work on some of those systems. So I think there's a pretty big range, actually, of what you can.
For the ytterbium compound, that's interesting in the context of the dynamical axion. I think it's ytterbium, barium, zinc oxide.
Oh, okay. So you're saying you actually watched as I zipped by those slides. Sorry. How do you quickly go through?
Oh, I'm just wondering how big the band gap is.
I don't know for that particular one. But also there's a reason that I should say, so I didn't say this because I didn't go through it. In the axion story, it's pretty speculative. So what the ingredients are here is two things which exist in different materials, but don't, as far as I know, exist in any current material together.
Right.
So the thing is that you need to have both T breaking and P breaking, and you want this to coexist with the spin-ice fractionalization in some way. So there's an entire sort of subfield in the last 5 or 10 years studying classical fragmented spin ices, where there's a coexistence between sort of pinch points, which correspond to this divergence-free condition, and some kind of ordering, which would be like a staggered charge ordering, so a little bit of all in, all out, or something in the background. And those classically exist, and this fragmented spin ices exist in the whole mu mirror data as believed. But that doesn't break inversion. So there is another class of materials which are called breathing pyrochlores, where the two sublattices, the A and B sublattices of the tetrahedra, are basically just different sizes. So that's the breathing, and that breaks inversion. And so if you could find a material which was a breathing pyrochlore with a spin half type or 2-level type easy axis spin, which also had the this coexisting order. So that's the thing. We don't actually know material where they're both there. Then you would have the symmetries to get the axion. And okay, so this is, like I said, the most speculative. We don't think it's crazy because both of those things exist separately, and this is a huge class of materials, but it's not in either of those specifically, or both ingredients aren't in any one of them.
Chris, what's the status of the, neutron scattering, experiments? I'm sure they have done some, they have results on some of these materials, right? So what do they see?
They see, continua that some of them they attribute to, they try to attribute to 2-particle continua, so spin-on fractionalization, but they're kind of just bands of stuff. So if you want to be critical, you'd say, oh, well, that could be from something else, right? Mm-hmm. And they don't have the resolution to resolve this stuff. So this level of detail is not there in any of the experiments that I looked at. Mm-hmm. It's, I've talked to some of the neutron scatterers. I don't think it's totally crazy to look for this, but they had to have a reason to go and look really carefully at Q equals 0 structure, because they, you have to do a lot of averaging. And so you have to decide that's what you want to look at, and then collect a lot of data near there and so on. They didn't have that in any particular incentive to go look at that before. So I don't think it's completely crazy, but it's not been done.
Mm-hmm. All right.
Yeah. And the other thing is, the other thing you could look for is, so if you look in the non-spin flip channel, in principle, you can see, forget this continuum up here, forget this axion stuff, but in principle, you could see like the photon dispersion. but the energy scale there is just very small. So it's easier to look at the spinons because there's a big gap to them and their bands are much bigger than to try to resolve anything about this, in principle, linearly dispersing mode, which you can couple to, but which is just at a very small energy, a ring exchange energy. So that in inelastic neutron scattering, I don't think anybody's seen real evidence for that. It's just not resolved enough.
All right. So if there are no other questions from the audience, let's thank Chris one more time. And we invite you to join us again next week for the last Quantum Art seminar of the year. Bye, Chris. Thank you.
Yep. Thanks. Thanks, everybody.